Hey guys, it's AJ from Design the Everything. Today I'm finally going to get around to doing the video where I discuss all of the engineering choices that have gone into designing the jet engine, or that will go into designing the jet engine. Now this video is going to be entirely engineering centric. If that's not interesting to you, feel free to skip it. I promise in the next video there will be plenty of flames, but there won't be in this video. So I was trying to figure out how to make this interesting, and so I did a PowerPoint, because that's what engineers do when they need to make presentations. But then I realized I couldn't watch my PowerPoint as I was talking into my camera because I need to see myself on the webcam. So I printed it off like I was 75. Hopefully, though, I'll have the words up on, like, right there, which is why I'm off-center in the camera. Whenever I start a project, particularly a complex project, I go through a series of steps. I start by defining the problem, defining what I consider success, defining my constraints or limitations, determining what I know and what I don't know, doing some incremental tests, then doing my full design, testing that design, and then fixing it if something's broken. And I'm going to go through those steps one by one in this video for you. So obviously, I don't need to actually be building a 3D printed jet engine. This is for fun, and I acknowledge that. So you'll just have to kind of bear with me with this problem statement because I just made it up. Normally, you would talk to your clients or your customers to figure out where all of this stuff is coming from. I've defined my problem as to design and build a jet engine primarily with 3D printed parts as a technology and educational demonstrator. So that brings us into, how do we know if it's actually working? How do we know if we have actually succeeded in solving that problem that we stated a second ago? We need some sort of criteria we can use to evaluate our design way down at the bottom of the process after we've already made it and we're in the testing phase. So for this project, I want it to be at least 75%, 3/4 3D printed, and run for at least 30 seconds. So I know I'm setting the bar kind of low on runtime, but I feel like that's the only way to make this practical. My only other criteria is I want it to provide its own air for combustion. However, I do not expect it to pressurize its own fuel. And so that's why I have this. This is actually an upgraded pump from the one I showed in my last few videos. I also don't expect it to run continuously over the full 30 seconds. My plan is to have it pulse the fuel for a second and ignite it, and then let it cool down, and then give it a little bit more fuel and ignite it, and then let it cool down. And that way, it's less likely to catch on fire as fast. It will still catch on fire eventually, but it'll wait longer before it does. I don't expect this to generate any usable thrust. I'm not building an airplane here. I just am building a demonstrator, as I said earlier. So as long as it spins and it's self-sustaining, I'm happy. So now let's talk about what's limiting me. We've already talked about the problem statement and how we're going to define a success. So now we need to know the limitations we're going to work with. To start with, obviously all of the 3D printed parts need to be smaller than my printer. Fortunately, I have a pretty big printer, so that's not going to be too much of an issue. All of the parts I print will be in PLA or ABS. I'm going to use PLA as much as I can, but if I have to use ABS, I will. The reason for that is that's what I have, that's what most people have, and it's the easiest to use. Yeah, there are some exotic filaments that are out there that could work better, but they're more difficult to use. A lot of times they're more toxic. And let's face it, if I really wanted to do this the easy way, I would not be 3D printing it. I also need to make sure that all of the 3D printed components are modular. That means they can easily be swapped out so that if one of them catches on fire, I can just reprint that one instead of having to reprint the whole thing. I don't know if you've noticed, but this is a fairly low budget operation. Literally my whole budget for the last year just bought this microphone and the camera, and if I'm going to buy anything else, I have to wait another year. So I'm not going to be pouring a lot of money in this project. Plus, I want this to be something else that someone else can build if they feel like setting their house on fire. So I'm going to try to keep the price at about $50 or below. Also, to speed up iteration time, I'm going to try to keep the total print time for the whole project under 36 hours. And a little pet peeve of mine, since I'm designing all of these parts to be 3D printed, there's no reason that they should have supports. Frankly, if you're designing a part that you know will be 3D printed and it has supports, it's generally sloppy design. So in all of my parts, I'm going to try to avoid that. And then lastly, I'm specifying alcohol as my fuel. And that's because it's cheap, it's readily available, and it burns cleanly. So I'm not going to be facing much in the way of fumes, except for my engine that's on fire. But that's a different story. Now that we know what our limitations are, we need to figure out what we don't know. And this can be pretty difficult, especially if we don't know that we don't know something. In fact, I'm sure that I don't know something, but there's something I can do about that. So what we need to do is focus on the things that we know that we don't know. And off the top of my head, I can think of 4 things. What is the best way to vaporize fuel? How do we mix the fuel and the air once the fuel has been vaporized? How do we ignite that mixture? And then how will the PLA and the ABS plastics hold up to that fire? And to determine all of those things, we have to do incremental tests. Now, if I had done these videos in the right order, we wouldn't have seen any of these incremental tests yet. If you've watched my last 2 videos, you have already seen me working on the nozzle, which is my solution to how do we vaporize the fuel. I'm pretty sure we have that down, which just leads us to the next couple of incremental tests that I'll do before I actually finish the design of the engine. We need to figure out how we're going to ignite the fuel, which will be next week's video. We need to figure out the mixture, more or less, of the fuel to the air that we'll need, and we're going to need to test the 2 different plastics for their flame and heat resistance. Once we have all of that, we can finish the whole design for the engine. Then once we have the full design, we can build it and we can test it based on the criteria we established earlier. And then we can make changes as needed until we have our finished design. There's certainly going to be a lot of little problems and a lot of little hiccups that are going to happen as I go through this process with you guys. And that's to be expected. That's just how engineering works. And don't worry, I'll show you my successes, but I'll also show you all of the problems that I run into over the course of doing this project. I started doing this series because I feel like a lot of YouTube channels and even just popular media does a really bad job of showing all of this work that goes into some of these engineering projects. There are a lot of fantastic projects out there where you only get to see the end result and you never get to see the process that goes in it. So this series is my answer to that, where you'll see all of my reasoning, all of my thought process, and all of my mistakes that will go into this engine. And honestly, at the end, I don't know if this engine will work. This is a hard thing to do. This is a dumb thing to do. This isn't how engines are made. But if it succeeds, it'll be just that much cooler because of the mistakes that went into it.